Can you imagine a moment before time itself existed? 13.8 billion years ago, there was nothing, no space, no light, no matter, not even the tiniest whisper of existence. And then, in a flash too brief to measure, everything ignited into being. Galaxies spiraled into life, stars blazed across the void, and every atom that makes you, came into being from a single, unimaginably small point. This isn't just a story of the universe. It's the story of everything that ever was, everything that is, and everything that ever will be. The moment of creation. Let's start at the beginning, though beginning is perhaps the wrong word. Before the Big Bang, there was no before. Time itself didn't exist. Space didn't exist. The very concepts we use to understand reality hadn't been invented yet by the universe. And then, roughly 30.8 billion years ago, something extraordinary happened. The Big Bang wasn't an explosion in space. It was an explosion of space itself. Imagine every point in the universe simultaneously expanding outward, creating space and time as it went. In that first, incomprehensibly tiny fraction of a second, the universe was smaller than an atom, yet it contained all the energy and potential that would eventually become everything we see around us today. The conditions in these earliest moments were beyond extreme. We're talking about temperatures so high that our familiar concepts of matter and energy completely break down. We're talking about densities so enormous that a volume smaller than the period at the end of this sentence contained more mass than entire galaxies would eventually hold. The universe was a roiling, seething cauldron of pure energy, where the laws of physics as we know them were still taking shape. This initial moment, sometimes called the Planck epoch, lasted for an almost unimaginably short time. We're talking about 10 to the power of negative 43 seconds. That's a decimal point, followed by 42 zeros, and then a 1. In this briefest of moments, the universe was so hot and so dense that even the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were unified into a single, all-encompassing force. The universe was, in a sense, perfectly symmetric, perfectly unified. But this perfect unity couldn't last. As the universe expanded, it cooled. And as it cooled, something profound happened. That single unified force began to separate, like a perfect crystal shattering into distinct pieces. First, gravity split off from the other forces. This happened when the universe was just 10 to the power of negative 43 seconds old. Then, as the universe continued to cool and expand, the strong nuclear force separated from what would become the electromagnetic and weak nuclear forces. Each of these separations, these symmetry breakings, fundamentally changed the nature of reality. Think about it like this. Imagine a perfectly smooth ball rolling down a hill. At the top of the hill, the ball could roll in any direction. It has perfect symmetry. But once it starts rolling, it picks one specific direction, breaking that symmetry. The universe went through similar transitions, except instead of picking a direction to roll, it was picking which fundamental forces would govern the behavior of matter and energy. Each choice, each symmetry breaking, was like the universe writing its own rulebook in real time. These earliest moments also set up one of the greatest mysteries in cosmology. Why is there something rather than nothing? In those first fractions of a second, the universe should have created equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate each other in a burst of energy, leaving nothing behind. If the universe had created exactly equal amounts of both, everything would have annihilated, leaving only a sea of radiation. But that's not what happened. For every billion antimatter particles, there were 1,000,000,001 matter particles. That tiny excess, that 1 in a billion difference, is why we exist today. Every atom in every star, every planet, every living thing exists because of this subtle imbalance. We are the remnants of an ancient cosmic battle between matter and antimatter, and matter won by the slimmest of margins. The first seconds, cosmic inflation, and the birth of forces. Now we come to one of the most revolutionary ideas in modern cosmology: cosmic inflation, proposed by physicist Alan Guth in 1980. Inflation theory suggests that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion that was faster than anything we can readily comprehend. We're talking about expansion faster than the speed of light. Not because anything was moving through space faster than light, but because space itself was expanding at this incredible rate. This inflation lasted for an almost incomprehensibly short time, somewhere around 10 to the power of -32 seconds. But in that brief instant, the universe grew by a factor that's hard even to express in words. The universe expanded by something like 10 to the power of 26 times its original size. To put that in perspective, if you took something the size of a single proton and inflated it by the same amount, it would be billions of light years across. The observable universe today, all the galaxies we can see, extending 46 billion light years in every direction, all of that emerged from a region that was originally smaller than the period at the end of this sentence. But why did this happen? What drove this incredible expansion? The answer lies in something called a scalar field, specifically the inflaton field. Think of this as a special kind of energy that filled all of space. This field was in what physicists call a false vacuum state. It was like a ball balanced precariously at the top of a hill, storing enormous amounts of energy in what seemed like empty space. This energy created a kind of negative pressure. And through the equations of Einstein's general relativity, negative pressure acts as a repulsive form of gravity. Instead of pulling things together like normal gravity, it pushed space apart, causing that exponential expansion. Inflation solves several major problems that plagued the original Big Bang theory. First, there's the horizon problem. When we look at the cosmic microwave background radiation, the afterglow of the Big Bang, we see that it has almost exactly the same temperature in every direction we look. The difference between the hottest and coldest spots is only about 1 part in 100,000. But according to the original Big Bang theory, without inflation, regions of space on opposite sides of the observable universe should never have been in contact with each other. They should never have had time to reach the same temperature. It's like finding that 2 kettles on opposite sides of the world somehow ended up at exactly the same temperature, even though they've never been connected. Inflation solves this by saying that before inflation, the entire observable universe was once a tiny region that was in thermal contact. All those regions could exchange energy and reach the same temperature. Then inflation suddenly blew this tiny region up to cosmic proportions, carrying those uniformly hot regions far apart from each other. So the cosmic microwave background is uniform because all those regions started out in contact before inflation separated them. Then there's the flatness problem. When we measure the geometry of the universe, whether it's curved like a sphere, curved like a saddle, or flat like a piece of paper. We find that it's remarkably close to being perfectly flat. In fact, it's flat to within 1% of perfect flatness. This is strange because, according to general relativity, a universe that starts out even slightly curved will become more and more curved as it evolves. For the universe to be as flat as we observe it today, it would have had to start out flat to an absurd degree of precision. We're talking about precision to 1 part in 10 to the power of 60. That's like balancing a pencil on its point and having it stay perfectly upright for billions of years. Inflation solves this problem through a simple mechanism: stretching. Just as inflating a balloon makes its surface appear flatter and flatter the bigger it gets, cosmic inflation stretched out any initial curvature in space until the universe became, for all practical purposes, perfectly flat. No fine-tuning required. Any initial curvature, no matter how extreme, gets inflated away. During this inflationary period, something else remarkable happened. Quantum fluctuations in the inflaton field were stretched to cosmic scales. Normally, quantum mechanics deals with the behavior of particles and energy on the smallest possible scales. But inflation took these microscopic quantum jitters and blew them up to galaxy-sized proportions. These quantum fluctuations became the seeds of all cosmic structure, the tiny variations in density that would eventually grow, through the force of gravity, into the galaxies, stars, and planets we see today. In a very real sense, the entire large-scale structure of the universe, all the galaxies and clusters and superclusters, began as quantum fluctuations, tiny ripples in the fabric of space-time that were magnified to cosmic proportions by inflation. As the inflaton field rolled down from its false vacuum state to its true minimum energy state, the exponential expansion came to an end. This process, called reheating, converted the enormous energy stored in the inflaton field into a hot soup of particles and radiation. The universe transitioned from being cold and empty, stretched out by inflation, to being hot and dense again, filled with particles and radiation. This marked the end of inflation and the beginning of what we might call the standard Big Bang expansion. At this point, the universe was still incredibly hot. We're talking temperatures of around 10 to the power of 15 degrees. That's a quadrillion degrees, far hotter than anything that exists anywhere in the universe today. At these temperatures, matter as we know it couldn't exist. Instead, the universe was filled with a plasma of fundamental particles: quarks, gluons, leptons like electrons, and the force-carrying particles like photons, and the force-carrying particles like photons, and the W and Z bosons. These particles were in a constant state of creation and annihilation, popping in and out of existence as energy converted to matter and back again. The 4 fundamental forces had now separated into their distinct identities. Gravity was doing its thing, pulling masses together. A strong nuclear force was binding quarks together, though they were still too hot to form stable particles like protons and neutrons. The electromagnetic force and the weak nuclear force had also separated, though they had only recently been unified in what's called the electroweak force. This separation happened when the universe was about 10 to the power of -10 seconds old, and it was associated with a field that permeates all of space, the Higgs field. The Higgs field gave mass to the fundamental particles, and its associated particle, the Higgs boson, was finally discovered at CERN's Large Hadron Collider in 2012, confirming this picture of how particles acquired mass in the early universe. As the universe continued to expand and cool, it reached a critical temperature, around 1 trillion degrees, where quarks could finally bind together to form protons and neutrons. This happened when the universe was about 1 microsecond old. Before this moment, quarks had existed in what's called a quark-gluon plasma, a state of matter so hot and dense that quarks couldn't be confined inside protons and neutrons. They roamed freely, bound only by the strong force mediated by particles called gluons. But as the temperature dropped below this critical threshold, quarks suddenly found themselves confined within protons and neutrons. This transition was like water freezing into ice, a phase transition where the nature of matter fundamentally changed. The formation of matter. From quarks to atoms, the universe continued its relentless expansion, cooling as it went. By the time it was about 1 second old, the temperature had dropped to about 10 billion degrees. Still incredibly hot by any standard, but cool enough for new processes to begin. This is when Big Bang nucleosynthesis kicked in, the formation of the first atomic nuclei. During nucleosynthesis, which lasted for about the first 3 minutes of the universe's existence, protons and neutrons began to stick together to form the nuclei of light elements. Primarily, this meant the creation of deuterium, a heavy form of hydrogen with 1 proton and 1 neutron, and helium-4, which has 2 protons and 2 neutrons. Small amounts of helium-3, lithium-7, and beryllium-7 were also created. This process is one of the great triumphs of Big Bang cosmology. When we calculate how much of each element should have been created based on the conditions in the early universe, and then look at the actual abundances of these elements in the oldest stars and gas clouds we can observe, the match is extraordinary. About 75% hydrogen and 25% helium, with just trace amounts of the other light elements. It's one of the most precise confirmations we have that the Big Bang theory correctly describes the early universe. But nuclear synthesis didn't create everything. Elements heavier than lithium, things like carbon, nitrogen, oxygen, iron, and all the other elements that make up planets and people, weren't created in the Big Bang. They had to wait for the first stars to form, where nuclear fusion in stellar cores would forge these heavier elements over billions of years. We are, quite literally, made of stardust, the products of nuclear reactions in stars that lived and died long before our sun ever formed. Throughout these early moments, dark matter was playing a crucial but invisible role. Dark matter doesn't interact with light, which is why we can't see it directly. But it does interact through gravity, and in the early universe it was already beginning to clump together under its own gravitational attraction. These clumps of dark matter would eventually become the gravitational scaffolding upon which all visible structure would form. Think of dark matter as providing the skeleton that supports the flesh and organs of the visible universe. Galaxies, as we'll see later, form inside these dark matter structures, their gas and stars pulled in by the gravitational wells created by dark matter concentration. Physicists estimate that dark matter makes up about 27% of the universe's total mass energy content, while the normal matter we're familiar with, the stuff that makes up stars, planets, and people, accounts for less than 5%. The rest, about 68%, is dark energy, which we'll explore in detail later. Dark matter is roughly 5 times more abundant than normal matter, which means the universe is largely made of something we cannot see or directly detect. We know it's there because of its gravitational effects. Galaxies rotate too fast for the amount of visible matter they contain. They would fly apart if there wasn't additional invisible mass holding them together. Galaxy clusters, too, contain far more mass than we can account for by adding up all their visible matter. Despite decades of searching, we still don't know what dark matter is made of. The leading candidates are WIMPs, weakly interacting massive particles, hypothetical particles that interact only through gravity and the weak nuclear force, making them incredibly difficult to detect. Recently, however, researchers announced a potentially groundbreaking discovery: a gamma-ray signal from the center of our galaxy that matches the expected signature of dark matter particles annihilating each other. If confirmed, this could be the first direct evidence of dark matter particles, potentially ending a century-long search and revealing one of the universe's deepest mysteries. Other candidates for dark matter include axions, extremely light particles that were originally proposed to solve a different problem in particle physics, and even primordial black holes formed in the earliest moments of the universe. The search continues, using sophisticated detectors buried deep underground to shield them from cosmic rays, satellite telescopes looking for signals from space, and particle accelerators trying to create dark matter in the lab. As the universe continued to cool, it reached another milestone. When it was about 380,000 years old, a mere cosmic eye blink compared to its current age of 13.8 billion years, the temperature had dropped to about 3,000 degrees, cool enough for electrons to combine with atomic nuclei to form neutral atoms. Before this moment, the universe had been opaque, filled with a fog of free electrons that constantly scattered light, preventing photons from traveling any significant distance. It was like trying to see through a thick mist. Light couldn't propagate freely, but when electrons combined with nuclei to form atoms, the universe suddenly became transparent. Photons could now travel through space without constantly being scattered. This moment is called recombination, and it's what created the cosmic microwave background radiation that we observe today. Those photons that were released when atoms formed have been traveling through space ever since, and we can detect them now as a faint microwave glow coming from every direction in the sky. This radiation has cooled as the universe expanded, redshifted from visible light down to microwaves, but it still carries information about the conditions in the universe at that moment, 380,000 years after the Big Bang. The cosmic microwave background is one of our most powerful tools for studying the early universe. Its temperature is remarkably uniform, 2.725 Kelvin, in every direction we look, with variations of only about 1 part in 100,000. These tiny variations, or anisotropies, are the imprints of those quantum fluctuations that were stretched to cosmic scales during inflation. They show us the distribution of matter and energy in the early universe, and by studying them in detail, we can determine fundamental properties of the cosmos: its age, its composition, its geometry, and even the primordial sound waves that once rippled through the hot plasma before atoms formed. The cosmic dark ages, when the universe went silent. After recombination, the universe entered a period that cosmologists call the cosmic dark ages, a somewhat ominous name for an era that lasted several 100 million years. This was a time when the universe was filled with neutral hydrogen gas, spread thinly through space, but no stars had yet formed. There were no galaxies, no glowing nebulae, no brilliant quasars, just darkness, punctuated only by the gradually cooling cosmic microwave background. But this wasn't a period of stagnation. Even though we call them the Dark Ages, enormous changes were underway beneath the surface of visibility. Dark matter, which had been clumping together since the earliest moments, was now creating deeper and deeper gravitational wells. These wells acted like cosmic magnets, pulling in the neutral hydrogen gas that filled the universe. Slowly, over millions of years, clouds of hydrogen began to accumulate in the centers of dark matter concentration. These accumulating gas clouds were the seeds of future galaxies, but they weren't yet massive enough or dense enough to ignite the nuclear fusion reactions that power stars. The gas needed to cool and collapse further, and the primary cooling mechanism during this era was molecular hydrogen, two hydrogen atoms bound together. When these hydrogen molecules collided with each other, they could radiate away some of their energy as infrared photons, allowing the gas clouds to cool and compress. This was a slow process. The Dark Ages weren't dramatic or eventful in the way later cosmic epochs would be, but they were essential. Gravity was doing its patient work, amplifying those tiny density fluctuations from the early universe into the hierarchical structure we see today. Small perturbations grew into larger ones. Regions that were slightly denser than average became even denser as their enhanced gravity pulled in more matter. This process of gravitational instability is what ultimately creates all cosmic structure. It's what transforms a nearly uniform universe into one filled with galaxies, clusters, and the cosmic web. The universe during the Dark Ages was cooling, expanding, and slowly organizing itself. The temperature of the cosmic microwave background was dropping, having started at 3000 degrees at recombination and cooling, to a few hundred degrees, and then to a few tens of degrees, as hundreds of millions of years passed. The universe was growing darker and colder, but also more structured. Those early gas clouds were growing more massive, pulling in more and more material from their surroundings. There's something almost poignant about this era. For hundreds of millions of years, the universe was dark and quiet, waiting for something to happen. All the ingredients for stars and galaxies were there, slowly coalescing in the dark. It's like a stage before a play begins. The props are being set up, the actors are in the wings, but the curtain hasn't yet risen. The Dark Ages were the universe holding its breath before the explosion of light and structure that was about to transform everything. The end of the Dark Ages came not with a gradual brightening, but with a sudden dramatic change. As gas clouds in the centers of dark matter halos grew denser and more massive, they eventually reached a critical threshold. When enough mass accumulated in a small enough volume, the gas at the center became hot enough and dense enough for nuclear fusion to begin. And when that happened, the first stars ignited, bringing light back to the cosmos. The first light. Birth of population through stars. The moment the first stars turned on marked the end of the cosmic Dark Ages and the beginning of cosmic dawn. A new era when the universe began to glow again with the light of stars. These first stars are called population 3 stars by astronomers, and they were nothing like the stars we see in the sky today. They were titans, monsters of the early universe. Population 3 stars formed from primordial gas composed almost entirely of hydrogen and helium, with only trace amounts of lithium. They had no heavier elements, no carbon, no oxygen, no iron, because those elements hadn't been created yet. And this lack of heavy elements had profound consequences for how these stars formed. In modern star formation, elements like carbon and oxygen act as cooling agents, radiating away energy and allowing gas clouds to cool and fragment into many smaller stars. But without these elements, the primordial gas clouds couldn't cool as efficiently. As a result, they formed much more massive stars. These first stars were likely tens or even hundreds of times more massive than our Sun. Some theoretical models suggest they could have been as massive as 300 solar masses or even more. To put that in perspective, the most massive stars in the present-day universe are typically only about 100 solar masses, and they're incredibly rare. The population 3 stars were a completely different breed, supermassive luminous giants that burned with incredible ferocity. Because of their extreme mass, population 3 stars were extraordinarily hot and luminous. They would have shone primarily in ultraviolet light, with surface temperatures reaching tens of thousands of degrees. The most massive among them would have been millions of times more luminous than the Sun. If you could somehow transport one of these stars into our night sky, at the distance of our Sun's nearest stellar neighbor, it would outshine Venus and appear as bright as the full moon. But these titans had short, violent lives. The more massive a star is, the more rapidly it burns through its nuclear fuel. While our Sun will live for about 10 billion years, these massive population 3 stars consume their fuel in just a few million years, sometimes in less than a million years for the most massive ones. They lived fast and died dramatically, ending their lives in spectacular supernova explosions that released more energy in a few seconds than our Sun will emit in its entire lifetime. These supernova explosions had a transformative effect on the universe. During their brief lives, population 3 stars fused hydrogen and helium into heavier elements in their cores: carbon, nitrogen, oxygen, silicon, and iron. When they exploded, they scattered these newly forged elements into space, seeding the surrounding gas clouds with the first metals. Subsequent generations of stars that formed from this enriched gas would be different, smaller, longer-lived, more like the stars we see today. This process of stellar nucleosynthesis and metal enrichment continues to this day, with each generation of stars adding more heavy elements to the cosmic mix. But the impact of population 3 stars went far beyond just creating heavy elements. Their intense ultraviolet radiation had the power to ionize hydrogen atoms, to strip electrons away from their nuclei. As these massive stars shone, they created bubbles of ionized gas around themselves, regions where the hydrogen had been transformed from a neutral, opaque state into an ionized, transparent plasma. These ionized bubbles expanded outward from each star and each cluster of stars, gradually eating away at the neutral hydrogen that filled the universe. This process is called cosmic reionization, and it was one of the most significant phase transitions in cosmic history. Before reionization, the universe was filled with neutral hydrogen that absorbed ultraviolet light, making the universe opaque to certain wavelengths of radiation. After reionization, the intergalactic medium became ionized and transparent, allowing light to travel freely through space. It's like the universe went from being filled with fog to being crystal clear. Reionization wasn't instantaneous. It unfolded over hundreds of millions of years, beginning when the first population 3 stars ignited around 200 to 400 million years after the Big Bang, and completing when the universe was about 1 billion years old. During this time, ionized bubbles around stars and early galaxies grew larger and larger, eventually overlapping and merging until the entire intergalactic medium was ionized. By the time reionization was complete, the universe had fundamentally changed. It had gone from dark to light, from opaque to transparent, from simple to structured. Recent observations from the James Webb Space Telescope have given us unprecedented views of this era. In 2024, JWST discovered a supernova that occurred when the universe was only 730 million years old, one of the most distant and earliest supernova explosions ever observed. This discovery provides direct evidence of massive star formation during the reionization era, confirming our theoretical models of how these early stars lived and died. Some researchers have even suggested that population 3 stars might have taken on even more extreme forms in regions with unusually strong radiation fields that dissociated molecular hydrogen. Gas clouds might have collapsed directly into supermassive objects tens of thousands or even hundreds of thousands of times more massive than the Sun. These supermassive dark stars, so called because they might have been powered by dark matter annihilation rather than nuclear fusion, could explain the puzzling presence of supermassive black holes in the very early universe. If these dark stars collapsed directly into black holes, they would provide ready-made seeds for the billion solar mass black holes we observe in quasars less than a billion years after the Big Bang. The first stars fundamentally transformed the universe. They brought light to the darkness. They created the first heavy elements. They ionized the intergalactic medium. And when they died, they left behind black holes and neutron stars, dense remnants that would play crucial roles in the subsequent evolution of galaxies. Every star you see in the night sky, every planet, every living thing, owes its existence to these primordial giants. They were the universe's first architects, laying the foundation for everything that would come after. Cosmic Noon. The universe's golden age. As the universe continued to evolve, it entered what astronomers call cosmic noon, an era roughly 2 to 3 billion years after the Big Bang, when star formation reached its peak across the cosmos. This was the universe's golden age, a period of frenetic activity when galaxies were rapidly assembling and stars were being born at a rate that would never be matched again. During cosmic noon, galaxies were forming stars at a rate roughly 10 to 100 times higher than the rate in galaxies today. The universe was ablaze with stellar birth. In many galaxies, about half of their total stellar mass formed during this relatively brief period. It was as if the universe was in its youth, vigorous, energetic, rapidly growing and changing. The galaxies that formed during this era looked very different from the majestic spiral and elliptical galaxies we see in the nearby universe today. They were smaller, more irregular, more turbulent. Many were undergoing intense bursts of star formation, with vast clouds of gas being converted into stars at remarkable rates. These galaxies were often disturbed and irregular in shape, lacking the calm, organized structures we see in mature galaxies. They were messy, chaotic, but incredibly productive. This was also a period of frequent galaxy mergers and interactions. Dark matter halos were colliding and merging, bringing their galaxies together in dramatic cosmic collisions. When galaxies merge, their gas clouds collide and compress, triggering intense bursts of star formation. Some galaxies during this era were experiencing what we call starburst activity periods, when they were forming stars hundreds or even thousands of times faster than the Milky Way does today. The supermassive black holes at the centers of galaxies were also growing rapidly during this period. As gas spiraled into these black holes, It heated up and emitted enormous amounts of energy in the form of intense radiation and powerful jets of particles. These active galactic nuclei, or AGN, shone so brightly that they could outshine their entire host galaxies. Some of them appeared as quasars, quasi-stellar objects that looked like stars but were actually supermassive black holes, billions of times more massive than the Sun, feeding voraciously on surrounding gas. The relationship between galaxies and their central black holes was becoming increasingly important during this era. Astronomers have discovered that the mass of a galaxy's central black hole is closely correlated with the mass of its bulge, the central concentration of stars. This suggests that black holes and galaxies somehow co-evolved, with each influencing the other's growth. When black holes are actively feeding and shining as quasars, their radiation can actually shut down star formation by heating and expelling gas from the galaxy. This feedback mechanism may be what eventually brings cosmic noon to an end in individual galaxies, quenching their star formation and allowing them to settle into more sedate middle age. The peak of cosmic noon occurred around 10 billion years ago, when the universe was about 3 billion years old, less than a quarter of its current age. By this time, the universe had already built up a significant population of galaxies, stars, and black holes. The large-scale structure was becoming increasingly apparent, with galaxies clustered together in groups and clusters, connected by filaments of dark matter and gas that form what we call the cosmic web. This cosmic web is one of the most striking features of the universe on large scales. If you could see dark matter, the universe would look like an enormous three-dimensional spider web, with dense nodes and filaments connected by tendrils of matter, all separated by vast empty voids. Galaxies live along these filaments and at the intersections where multiple filaments meet. The largest structures in the universe, galaxy clusters and superclusters, form at these intersections, containing thousands of galaxies bound together by their mutual gravity. Recent discoveries have revealed structures so large they challenge our understanding of cosmic evolution. In 2024, astronomers announced the detection of the giant arc and the Big Ring, enormous structures spanning hundreds of millions of light-years across space. These megastructures appear to violate the cosmological principle, the assumption that the universe is roughly homogeneous on large scales. Their existence suggests that we still don't fully understand how structure formed in the early universe, and that there may be physical processes at work that current models don't account for. After cosmic noon, star formation began to decline across the universe. Galaxies consumed and expelled much of their gas, leaving less fuel for new stars. The merger rate decreased as the universe expanded, and galaxies became more separated. Black hole feedback became more efficient at preventing new star formation. The universe was transitioning from vigorous youth to comfortable middle age. Today, billions of years after cosmic noon, the overall rate of star formation in the universe is more than 10 times lower than it was at its peak. The universe is slowly growing darker and quieter as fewer and fewer new stars are born. The architecture of cosmos, dark matter, and dark energy. Throughout the history we've been tracing, two mysterious components have been silently shaping cosmic evolution: dark matter and dark energy. Together, they make up about 95% of the universe. Yet we know remarkably little about what either of them actually is. Understanding these invisible components is crucial to understanding not just the universe's past, but its future. Let's start with dark matter, which makes up roughly 27% of the universe's total mass energy content. We've mentioned it several times already, but it's worth diving deeper into what we know and what we don't know about this mysterious substance. Dark matter doesn't emit, absorb, or reflect light, which is why we can't see it directly. But it does interact through gravity, and its gravitational effects are unmistakable. The evidence for dark matter is overwhelming and comes from multiple independent sources. Galaxy rotation curves provide some of the most direct evidence. When we measure how fast stars are orbiting in spiral galaxies, we find something strange. The stars in the outer regions are moving much faster than they should be, based on the visible matter we can see. According to Newton's laws of gravity, stars far from the galactic center should be orbiting more slowly, just as the outer planets in our solar system orbit more slowly than the inner ones. But that's not what we observe. Instead, the rotation speed remains roughly constant even in the outer parts of galaxies, which can only be explained if there's a huge halo of invisible matter extending far beyond the visible disk. Galaxy clusters provide even more dramatic evidence. When we look at clusters of galaxies, we can measure their total mass in two ways: by adding up all the visible matter in stars and gas, and by measuring how they gravitationally bend light from more distant objects, a phenomenon called gravitational lensing. The mass we infer from gravitational lensing is typically 5 to 10 times larger than the visible mass. Something invisible is providing the extra gravity needed to hold these clusters together and to bend light so dramatically. Perhaps the most striking evidence comes from colliding galaxy clusters. The most famous example is the Bullet cluster, where two galaxy clusters have collided and passed through each other. When we map out where the visible matter is using X-ray observations, we see that the hot gas, which makes up most of the visible mass, has been slowed down by the collision, creating a shock wave. But when we map out where the mass is using gravitational lensing, we see that most of the mass passed straight through, unaffected by the collision. This invisible mass is dark matter, and its behavior in these collisions shows that it must be made of particles that interact very weakly with normal matter, weakly enough that two clouds of dark matter can pass right through each other without colliding. But what is dark matter made of? Despite decades of searching, we still don't have a definitive answer. The leading candidate has long been WIMPs, weakly interacting massive particles. These are hypothetical particles that are perhaps 100 times more massive than a proton and interact only through gravity and the weak nuclear force. Experiments have been searching for WIMPs by looking for the rare occasions when a dark matter particle might collide with an atomic nucleus in a sensitive detector. So far, despite increasingly sensitive experiments, no one has definitively detected a WIMP. This has led physicists to consider alternative candidates. Axions are another possibility: extremely light particles, much lighter than electrons, that were originally proposed to solve a different problem in particle physics. Recent experiments are searching for axions by looking for their expected conversion into photons in strong magnetic fields. Another intriguing possibility is that dark matter isn't a new type of particle at all, but rather primordial black holes formed in the earliest moments of the universe. In late 2025, researchers analyzing data from the Fermi Gamma-ray Space Telescope announced what might be a breakthrough: a gamma-ray signal from the center of our galaxy that matches the expected signature of dark matter particles annihilating each other. If this signal is confirmed and can't be explained by other astrophysical processes, it could represent the first direct detection of dark matter particles. The energy spectrum of the gamma rays, their spatial distribution, and their intensity all match predictions for WIMPs with masses about 500 times the proton mass. But the physics community is cautious. Extraordinary claims require extraordinary evidence, and there are other possible explanations for the signal that need to be ruled out. Now let's turn to dark energy, which is even more mysterious than dark matter. Dark energy makes up about 68% of the universe, and its effects are cosmic in scale. While dark matter pulls things together through gravity, dark energy seems to push things apart, causing the expansion of the universe to accelerate. The discovery of dark energy was one of the biggest surprises in cosmology. In the late 1990s, two teams of astronomers were studying distant supernova explosions, using them as standard candles to measure cosmic distances and determine how the universe's expansion rate has changed over time. Everyone expected to find that the expansion was slowing down due to the gravitational attraction of all the matter in the universe. Instead, both teams found something shocking. The expansion was speeding up. Distant galaxies weren't just moving away from us. They were accelerating away, pushed by something that acts like a repulsive form of gravity. This mysterious component was dubbed dark energy, and its existence has been confirmed by multiple independent observations. We see its effects in the cosmic microwave background, in the large-scale distribution of galaxies, and in the way galaxy clusters have evolved over cosmic time. The simplest explanation for dark energy is that it's a property of space itself, the cosmological constant that represents the energy density of the vacuum. Einstein actually introduced a cosmological constant in his equations of general relativity, though for different reasons, and it acts exactly like dark energy, a form of energy that's the same everywhere and doesn't dilute as the universe expands. But recent observations are suggesting that dark energy might be more complicated than a simple constant. Data from the Dark Energy Spectroscopic Instrument, or DESI, which has mapped millions of galaxies across cosmic time, hints that dark energy might be evolving, getting stronger or weaker over time. If confirmed, this would be revolutionary. An evolving dark energy could be related to a new type of field permeating space, similar to the inflation field that drove cosmic inflation, but operating in the present-day universe. Some theoretical models suggest this could be connected to ultralight axions or other exotic particles. Even more speculatively, some researchers have proposed that dark energy might actually be connected to black holes. According to this idea, when massive stars collapse to form black holes, the matter doesn't just compress to a singularity. Instead, it converts back into a form similar to dark energy, coupling to the expanding universe. As the universe expands, these black holes would grow, and their accumulated dark energy would contribute to cosmic acceleration. It's a radical idea that challenges our understanding of both black holes and cosmology. But intriguingly, observations from DESI seem consistent with this model. The nature of dark energy has profound implications for the universe's future, which we'll explore shortly. But first, we need to discuss how these discoveries are forcing us to reconsider even our most basic theories. Modern observations. What James Webb Telescope has revealed. The launch of the James Webb Space Telescope in December 2021 marked the beginning of a new era in observational astronomy. With its massive 6.5-meter primary mirror and suite of sensitive infrared instruments, JWST can peer deeper into space, and therefore further back in time than any telescope before it. The observations it has returned are nothing short of revolutionary. and in many cases, deeply puzzling. One of JWST's primary missions was to study the first billion years of cosmic history, to see the earliest galaxies forming, to witness cosmic reionization in action, to potentially detect the signatures of population 3 stars. The expectation was that these early galaxies would be small, faint, and relatively simple, cosmic infants still in the process of forming. But that's not what JWST found. Instead, JWST revealed a universe that was already surprisingly mature at very early times. Galaxies appeared earlier, grew faster, and became more massive than theoretical models had predicted. In May 2024, JWST discovered a galaxy that existed just 290 million years after the Big Bang, making it one of the most distant galaxies ever observed. This galaxy, designated JIDES JS14-0, wasn't just distant. It was massive and bright, far more so than galaxies that young were supposed to be. Other observations found similar results. By August 2025, JWST had identified 300 unusually bright objects in the very early universe, appearing when the universe was less than 1 billion years old. Many of these objects were brighter than they should be, based on standard models of galaxy formation. Some appeared to be galaxies that had already accumulated hundreds of millions or even billions of solar masses in stars, despite having had only a few 100 million years to form them. It was as if the universe had somehow grown up too fast. This created a potential crisis for the standard model of cosmology. If galaxies could become so massive so quickly, it might suggest that something is fundamentally wrong with our understanding of how structure forms in the universe. Some researchers initially suggested that the Lambda CDM model, the standard cosmological model incorporating dark matter and dark energy, might need major revision. There was even speculation that JWST had broken cosmology. However, as more detailed observations accumulated, a more nuanced picture emerged. Many of these early bright objects turned out to be less massive than they first appeared. What made them so bright wasn't necessarily an extraordinary mass of stars, but rather active supermassive black holes at their centers. The intense radiation from matter falling into these black holes made the galaxies appear much brighter and more massive than they actually were. When researchers carefully accounted for this, they found that many galaxies were consistent with standard models after all. But not all of them. Even after accounting for active black holes, there are still more bright galaxies in the early universe than models predict. Star formation might have been more efficient in the early universe than it is today. The initial mass function, the distribution of masses for newly formed stars, might have been different in primordial gas. There might have been more massive stars forming, which would make galaxies brighter for a given mass. Or there might be physical processes we haven't properly included in our models. One of the most intriguing discoveries has been the little red dots population of small, extremely red objects found at high redshifts. For a long time, astronomers weren't sure what these were. Were they compact galaxies? Young quasars? Something entirely new? Recent analysis suggests many of them might be a new type of object. Compact galaxies dominated by supermassive black holes that are actively accreting material. These objects challenge our understanding of how supermassive black holes grow, because they seem to contain black holes that are far too massive for their host galaxies, based on local relationships between black hole and galaxy mass. JWST has also provided remarkable insights into cosmic reionization. The telescope discovered a galaxy, JWST 113-1, that existed just 330 million years after the Big Bang and was already emitting strong hydrogen emission lines. This was surprising because such emission should have been absorbed by the neutral hydrogen that filled the intergalactic medium at that time. Somehow, this galaxy or its neighbors had already carved out a large bubble of ionized gas around themselves, allowing this light to escape. This suggests that reionization might have proceeded in a complex, patchy way, with different regions becoming ionized at different times. In another groundbreaking observation, JWST identified dozens of small, low-mass galaxies that played an outsized role in reionization. These ultraviolet factories were punching well above their weight, emitting enormous amounts of ionizing radiation despite their modest sizes. Observations showed these galaxies existed in sufficient numbers and produced enough ultraviolet light to drive cosmic reionization, solving a long-standing puzzle about whether there were enough sources to ionize the entire universe. Perhaps one of the most profound observations came in December 2025, when JWST detected a supernova explosion in a gamma-ray burst that occurred when the universe was only 730 million years old. This observation provided direct, unambiguous evidence of massive stars dying in the early universe, confirming that population 3 or early population 2 stars were indeed forming and exploding as supernovae during the reionization era. The supernova's light curve matched those of similar explosions in the present-day universe, suggesting that despite forming from more pristine gas, these early supernovae weren't dramatically different from modern ones. JWST has also revealed that some early galaxies were feeding on cold gas streaming directly into them from the intergalactic medium. 3 galaxies observed when the universe was only 400 to 600 million years old were surrounded by dense clouds of almost purely primordial hydrogen and helium. This cold gas was falling onto the galaxies, fueling their rapid star formation. These observations provide direct evidence for the theoretical models of galaxy formation, showing that early galaxies grew by accreting cold gas from their surroundings. The telescope has even found hints of something even more exotic: potential signatures of dark stars, hypothetical objects powered by dark matter, annihilation rather than nuclear fusion. If confirmed, these would represent the first direct observational evidence of dark matter beyond its gravitational effects. However, this interpretation remains highly speculative and controversial. What's clear from all these observations is that the early universe was more complex and interesting than we expected. Galaxies formed quickly, black holes grew rapidly, stars were being born at prodigious rates, and cosmic reionization proceeded in a patchy, inhomogeneous way. JWST hasn't broken cosmology, but it has revealed that our models need refinement. The universe is teaching us that nature is often more creative and complicated than our theories give it credit for. The mysteries we still face. Despite more than a century of progress in cosmology, from Einstein's general relativity to the discovery of dark energy, fundamental mysteries remain. These aren't minor details or loose ends. They're deep questions that strike at the heart of our understanding of the universe. Perhaps the most pressing mystery in cosmology today is called the Hubble tension. When we measure how fast the universe is expanding, quantified by the Hubble constant, we get different answers depending on how we make the measurement. If we look at the cosmic microwave background and use our best models of the early universe to extrapolate forward, we calculate a Hubble constant of about 67 kilometers per second per megaparsec. But if we measure it directly by observing the motions of nearby galaxies and using standard candles like supernovae, we get about 73 kilometers per second per megaparsec. This might not sound like a big difference, but it's statistically significant. The measurements disagree by much more than their estimated uncertainties. This tension has persisted and grown stronger as observations have become more precise. It's not just a measurement error or a systematic problem with one technique. Both methods have been checked and rechecked by independent teams, and the discrepancy remains. So what does it mean? There are several possibilities, none of them entirely satisfying. Maybe there's something wrong with our understanding of the early universe, and the cosmic microwave background measurements need to be reinterpreted. Maybe there's new physics at work in the late universe that affects the expansion rate. Some theorists have proposed early dark energy or form of dark energy that was present in the early universe but has since decayed away. This could potentially resolve both the Hubble tension and explain some of JWST's unexpected observations of massive early galaxies. Another possibility is that our cosmological model needs fundamental revision. The standard lambda CDM model has been incredibly successful at explaining observations, but it makes some strong assumptions about the homogeneity and isotropy of the universe. Maybe on very large scales or at very early times, these assumptions break down. Some physicists have suggested modifications to general relativity itself, though these proposals face significant theoretical and observational challenges. The Hubble tension has even led some researchers to revisit long-abandoned ideas. One such idea is the tired light theory, proposed nearly a century ago by Fritz Zwicky. According to this theory, light doesn't lose energy because of the universe's expansion. Instead, photons gradually lose energy as they travel through space, perhaps through interactions with particles or fields. This would make distant objects appear redshifted without requiring cosmic expansion. For decades, this idea was rejected because it couldn't explain several key observations, particularly the cosmic microwave background and the evolution of galaxy properties with redshift. However, a 2024 study by researcher Leo Shamir used observations of more than 30,000 galaxies to test this idea. The results showed patterns in galaxy redshifts that seemed consistent with tired light rather than pure cosmic expansion. When the data was analyzed in a way that accounted for Earth's motion through space, the redshifts behaved exactly as tired light theory would predict. This has reignited debate about whether cosmic expansion really works the way we think it does, though most cosmologists remain skeptical and point out that tired light still can't explain many other observations. Even more radical alternatives have been proposed. In 2025, researchers from the University of Portsmouth suggested that our universe might have formed not from a Big Bang, but from the collapse of matter into a black hole in a larger parent universe. According to this black hole universe model, what we perceive as the Big Bang might actually be a bounce that occurred inside a black hole, where quantum effects prevented the formation of a singularity. This model attempts to avoid the infinity problems that plague standard Big Bang cosmology by replacing the initial singularity with a quantum bounce. Another recent proposal suggests that gravitational waves, ripples in spacetime itself, might have been the primary driver of cosmic structure formation, rather than quantum fluctuations stretched by inflation. According to this model, gravitational waves from the earliest moments of the universe interacted and built up complexity over time, eventually leading to the formation of galaxies and large-scale structure. The model makes specific predictions that could potentially be tested with future observations of gravitational waves and a cosmic microwave background. There's even a theory that challenges the existence of dark matter and dark energy altogether. Physicist Rajendra Gupta has proposed a model that combines covariant coupling constants with tired light to explain cosmic observations without requiring any dark components. According to this model, what we interpret as dark matter and dark energy are actually effects of the fundamental forces of nature weakening over cosmic time. The model suggests the universe might actually be 26.7 billion years old, nearly twice as old as the standard estimate, though this claim faces significant skepticism from the astrometrical community. The nature of dark matter itself remains one of the deepest mysteries. Despite compelling gravitational evidence for its existence, we still don't know what it's made of. The recent gamma-ray signal from the galactic center is tantalizing, but it could also be explained by other astrophysical processes. We need more data and independent confirmation before we can be sure we've actually detected dark matter particles. Dark energy presents an even deeper puzzle. Why does it have the value it does? According to quantum field theory, the vacuum energy, which is what dark energy might be, should be enormous, roughly 10 to the power of 120 times larger than the observed value. This discrepancy, called the cosmological constant problem, is perhaps the worst prediction in all of physics. We have no good explanation for why dark energy is so small, yet not exactly zero. The fact that dark energy density is comparable to matter density in the present epoch, neither vastly larger nor vastly smaller, seems like a remarkable coincidence that might hint at some deeper connection we don't yet understand. Then there are the questions about the very earliest moments. What happened at the instant of the Big Bang itself? What came before, if anything? Was there really a beginning, or has the universe existed eternally in some form? These questions push at the boundaries of physics, where our current theories break down. General relativity predicts a singularity at the beginning, a point of infinite density and temperature, where the equations simply stop making sense. But most physicists believe this singularity is an artifact of our incomplete understanding, not a real feature of nature. To truly understand the Big Bang, we probably need a theory of quantum gravity, a framework that unifies general relativity with quantum mechanics. String theory, loop quantum gravity, and other approaches are attempting to provide such a framework, but none has yet succeeded in making concrete, testable predictions about the very early universe. Until we have a complete theory of quantum gravity, the true nature of the Big Bang, and perhaps its cause or precursor, will remain one of science's greatest mysteries. The future of the universe. After tracing the universe's extraordinary journey from its violent birth in the Big Bang to the richly structured cosmos we observe today, a deeper and more unsettling question inevitably arises. What happens next? Is the universe heading toward a grand finale, or will it drift endlessly into the future? The answer to this question lies largely in one of the greatest mysteries of modern physics, dark energy, and more importantly, how it behaves over vast stretches of cosmic time. Dark energy appears to be a property of space itself, a kind of invisible pressure that drives the expansion of the universe to accelerate rather than slow down. If dark energy remains constant, if it truly is a cosmological constant, representing a fixed energy density woven into the fabric of empty space, then the fate of the universe is already written. Expansion will not merely continue, it will speed up forever. As billions of years pass, galaxies beyond our local neighborhood will recede from us at ever-increasing speeds. Eventually, the expansion of space between us and those distant galaxies will become so extreme that their light can no longer reach us. This does not violate Einstein's cosmic speed limit, because the galaxies themselves are not moving through space faster than light. Space itself is stretching between us. One by one, entire galaxies will slip beyond our cosmic horizon, fading into permanent invisibility. Future astronomers, if any remain, will see fewer and fewer galaxies in the night sky until only the remnants of our local group remain. Over immense timescales, the universe will grow darker and emptier. The large-scale cosmic web of galaxies will thin out, and vast regions of space will become almost entirely devoid of matter. What was once a universe filled with light, motion, and structure will gradually become a cold, silent expanse. This accelerated expansion also has profound consequences for the life cycle of stars. Stars are born when clouds of hydrogen gas collapse under gravity, igniting nuclear fusion in their cores. But hydrogen, the fundamental fuel of stars, is finite. As galaxies age and gas supplies are depleted, star formation will slow dramatically. Fewer new stars will ignite, and those that do will tend to be smaller, dimmer, and longer-lived than the brilliant giants of the early universe. Eventually, star formation will come to an end altogether. Existing stars will exhaust their nuclear fuel and fade away, leaving behind stellar corpses, white dwarfs, neutron stars, and black holes. Spiral galaxies will lose their graceful arms, becoming collections of aging stars, orbiting in silence. The night sky, once ablaze with light, will grow increasingly dim. Trillions of years into the future, even the longest-lived red dwarf stars will finally burn out. With no new stars being born, the universe will enter what scientists call the dark era. Light will become rare, generated only by occasional events such as black holes consuming matter or the slow decay of exotic particles, if such processes occur at all. If dark energy remains constant, this slow fading does not end in a dramatic collapse or explosion. Instead, the universe drifts toward a state known as heat death, a condition of maximum entropy, where energy is evenly spread out and no meaningful work can be done. Motion continues, particles still exist, but nothing significant ever happens again. In this vision of the future, the universe does not end with a bang, but with a whisper, an endless cold expansion into darkness, where time stretches on without events. And the once vibrant cosmos becomes a vast silent grave of its former brilliance. Thanks for watching this whole video.